We're going to start the brain stem. That's the first part of the brain that we're going to talk about. This is the brain stem right here. So this bracket is the brain stem. This part is the midbrain. This with the bulge is the pons. And then this is the medulla oblongata. It's continuous with the spinal cord, which is right here. Remember this to fill out, and label is on plus portal. So starting with the Word document and the PowerPoints, we have the medulla oblongata is the first thing we're going to talk about. Remember, it's the inferior most part of the brain stem. So it's continuous with the spinal cord itself. This picture is the picture that you have on PowerPoint. Okay, so here's the spinal cord and here's the medulla oblongata. And you haven't, you've probably heard about different things about the medulla, but it contains mainly ascending tracts coming from the spinal cord and then descending tracts going from the brain to the spinal cord. There are two major nuclei. Now remember, nuclei are gray areas in white matter that are concentrated dendrites and cell bodies. They're kind of our thinking area. So if you have a medulla oblongata, which is just the brain stem, you can have a heart rate and force of the heart by the cardiovascular center. It also controls the diameter of blood vessels, so think blood pressure, but it is not, steady. Like you wouldn't think of it totally controlling the heart or totally controlling the blood vessels or the blood pressure. The medullary rhombonicity area adjusts rhythm of breathing and others, so it has think about respiration. So again, if you just have the medulla oblongata, you are able to breathe and you are able to have a heartbeat. This is huge whenever we talk about quality of life and things like that, because a lot of times people just have a brain stem, but they're able to still breathe and have a heartbeat on their own. But if you look, they're able to do other things like touch, pressure, and feel vibration. They can have certain reflexes, such as coughing and vomiting and swallowing. They receive input from some cranial nerves, but damage to this will lead to death. Like I said, it interferes with the other things going up. I don't know if y'all remember the case of Terry Schiavo, but she responded to stimuli such as you would see in the medullary rhombonicity area. And the husband wanted to go ahead and take her off feeding tubes and water, and the parents did not because they said she responded. And the judges deemed that she was responding through the medulla oblongata, and they did discontinue the feeding tube and the water. So that's the medulla oblongata. Then you have the pons, which is the right next to the medulla, going superiorly. Above that, and it's anterior to the cerebellum, so it's in front of the cerebellum. It contains nuclei and tracts also. But when you think about what's it doing, think about it connecting the tracts that are going to the cerebral hemisphere into the cerebellum. Think about it coordinating things such as voluntary movements to the cerebrum, to the cerebellum. The cerebellum kind of says, well, this is where I'm at in space and time, and this is how you're going to get there. And the cerebrum is saying, this is what I want to do. It does help in some breathing control, and again, some cranial nerves go into the pons. Then the third part of the brainstem is the midbrain. It does a direct connection to the diencephalon. Remember, that's the part that we cannot see unless it's cut in a mid-sagittal section. It contains some large tracts. They're called the cerebral peduncles. So we've got a sensory one and we have a motor one. So the motor axons are coming from the cerebrum after it's told what to do to the spinal cord and the medulla and the pons. The sensory neurons are coming from the medulla and the thalamus. In other words, it's going up from the medulla all the way up to the thalamus, and the thalamus is going to go and send it to the cerebrum if it needs to go. So think of sensories coming up the spinal cord through the midbrain, and the midbrain sending it on its way, and the motor coming down from the cerebrum and sending it down to the spinal cord to get a response. There are two major nuclei in the midbrain also. They're the substantial niger, which are large and darkly pigmented, which niger means black, so that's what they look like. Whenever people have Parkinson's, this is the area that they have trouble with. Loss of that area, or loss of the use of that area, is associated with Parkinson's. Whereas the red nucleus, another nuclei within the midbrain, is connected with, it has a lot of blood supply and iron containing pigment. The cerebellum coordinates muscular movements through this. So again, the cerebrum and the cerebellum work together for our movement coordination after the cerebrum decides what it needs to do. There are some cranial nerves associated with the midbrain. Also, it has colliculae, which are 4 of them. There's 2 posterior bumps that are on the surface. I should say the bumps are on the posterior side of the midbrain itself. There's 2 superior. So I always think the 2 superior are working the eyes. They make our pupils dilate and constrict. That's the pupillary reflex. And they also make accommodation happen. Think of accommodation as moving the eyes so that you see one image. The 2 inferior, so think lower, is auditory, or the ear. So that's what makes us jump to loud noises, and it goes from the thalamus to the ear as far as our reflex responses go. The one other last thing that the brainstem does is it contains a reticular formation. It's also called this down here, reticular activating system. It's really kind of cool. They have small bundles of myelinated axons, and they have both ascending and descending tracks. So the reticular activating system is actually what has responsibility for consciousness. If you're in a coma, this is kind of what's broken. It is active when we're awake. I'm so sorry. It's active while we are awake, but when we go to sleep, it controls what goes up to the cerebrum. So mainly whenever we think about the ascending track, it's waking up the cerebrum if we want to become conscious. In coma patients, they cannot wake up the cerebrum. The descending tracks help regulate muscle tone. Let's go back to it, waking up the cerebrum. Sometimes, a loud noise might not wake you up, but a small, unusual noise might. That's because the RAS in the midbrain is allowing those tracks to go up to the cerebrum and tell you that there's a small, unusual noise. Whereas if the loud noise is something that the RAS is used to, it will not. They say that you always know what time it is, and like when you wake up, you can kind of guess what time it is because your midbrain is always tracking information, but it's not letting it always go up to the cerebrum, only what it deems is important. So if somebody's in a coma, they never get the signal to wake up the cerebrum. When we're asleep, we often get woken up for the signal through to the cerebrum that this is unusual, you need to wake up and pay attention. And that's everything in the midbrain, guys. Remember, you've got a picture here and here. This one is the one I'm talking about. Okay. Talk to you later. Next time it's going to be the diencephalon, that hidden brain.